Hello there. In this video, we're going to describe a lot of important concepts that are really important when understanding all of the different mechanics of pre-calculus. So you should already be comfortable with the notion of what a function means. So we have two sets, say A and B, typically referred to as the domain and the range of some mapping, say F. And this mapping F, also sometimes referred to as a relation, sends an element x to an element y in the range. And we call this mapping or relation F a function if there exists a unique element in the range that is mapped from x for all values x in the domain. So in this video, we're going to be primarily focusing on the idea of an inverse function, which pretty much performs the opposite action of taking the element y and mapping it back to x. And we will denote this by f to the exponent power -1, but we're going to mention that in a little bit more detail as well. All right, so firstly, let us assume that f is a function or a relation that is a function. So it maps every element in its domain to a unique value in its range. So this little function f with this -1 has the property such that if f of x is equal to y, so y is the image of x underneath this mapping f, then we write that f inverse of y is equal to x. So x is the image of y underneath this mapping f inverse. So these two mappings, f and f inverse, definitely do share some relations. Now before we actually get into the theoretical understanding of this thing, I need to make a really important thing clear because I often see this in social media and so on. So when you see this expression, this is not the same as 1 divided by f of x. So this expression on the right is the same as writing f of x to the power of -1. So this right-hand side is usually what we refer to as the multiplicative inverse of f of x. And this right-hand side, usually people just call it the inverse of f of x, but some people want to be a little bit more clear when they say inverse because there's additive inverse, multiplicative inverse, and so on. Some people will refer to this as the compositional inverse of f of x. And once we actually look in the details of the theoretical concepts of this, you'll actually understand why some people refer to it as the compositional inverse of f of x. All right, so let's go back to this point that I made above. So f sends the element x to the element y, and f inverse sends the element y to the element x, right? So x belongs to the domain of f, and y belongs to the range of f. Here, y belongs to the domain of f inverse, and x belongs to the range of f inverse. Now keep in mind these elements x and y are arbitrary. I'm not really assigning them to different elements. So if this function f inverse is truly the inverse, the compositional inverse of this function f, then we do have this property that if x is in the element of the domain of f, then x must be in the range of its compositional inverse, and if y is in the range of a function, then y is going to be in the domain of its compositional inverse, provided that this compositional inverse does exist, which we will definitely get to. But from this property, you may be able to see how you may be able to solve equations with these expressions. So if f of x is equal to y, and if f inverse of y is equal to x, what we can do is pretty much replace x in this expression, f of x equals y, with f inverse of y. So if that is the case, then we have f composed of f inverse of y is equal to y. In a similar fashion, we can replace this element y with f of x, and we're going to get that f inverse of f of x is equal to x. So we have these two statements. Now keep in mind again, y, which of course notice it's on the interior and also the output of this compositional function. Same thing goes for x here. In these two contexts, x and y are pretty much just dummy variables. We're not really given any meaning to them. So technically in this statement, I can rewrite this as f of f inverse of theta is equal to theta, and f inverse of f of theta is equal to theta. These thetas need not be equal, but they can be because nonetheless they are the same exact thing. So if that is the case, then we get a beautiful identity in this statement, right? So if f and f inverse are compositional inverses of one another, then we have the identity f inverse of f of x is equal to f of f inverse of x is equal to x. And this actually does have some graphical interpretations as well, which we will discuss. Now let's do a quick algebraic example of what an inverse actually does. So let's look at the function f of x is equal to 3x minus 2. So it's very easy to calculate, say, f of 2 is going to be equal to 3 times 2 is 6 minus 2 is 4. So if f were to have a compositional inverse, then if f of 2 is equal to 4, then f inverse of 4 would be equal to what? So if you said 2, you are correct. All right, so is there an actual algebraic function so that I can plug 4 in and get 2 as the output? And pretty much I can do that for any real number. So if I throw in 3, here I'm going to get 3 times 3 is 9 minus 2 is 7. So I should be able to plug 7 into this function and get 3 as the output. So maybe there's a function algebraically that has that particular structure, right? So let us replace f of x as the output of a particular arbitrary value x, and let's call that value y. So y, which I'm going to define as the output of arbitrary value x, so this is going to be equal to 3x minus 2. And I'm going to solve this equation for x, and you'll understand why in just a moment. So solve for x. So if I do that, I'm going to add 2 and divide by 3. So I'm going to get x is equal to y plus 2 all divided by 3, which is the same thing as writing 1/3 y plus 2/3 if I really want to do it. So remember, if f inverse is the compositional inverse of f, then the domain values is equal to the range values of its inverse, and the range of f is equal to the domain values of its inverse. And remember, typically we associate x values with the domain and y values with the range, and the range of this is going to be x. So pretty much what they do is they swap positions, right? So if we want a multiplicative representation, pretty much all we need to do is just replace x with y and y with x, and that is going to give us, if it exists, the functional representation of the compositional inverse of the original function. So using this expression, we can say that f inverse of x is equal to 1/3 x plus 2/3. And this is our claim to be the compositional inverse of f of x is equal to 3x minus 2. So we can test it at least with our 2 points, right? So we already said that f of 2 was equal to 4. So let's plug 4 into this inverse and see what we get. So f inverse of 4 was equal to 1/3 times 4 plus 2/3. So we have 4/3 plus 2/3. That's going to be 6/3, which is equal to 2. So that checks out. And we also said what? So f of 3, that was equal to 7. So let's plug 7 into this. So that's going to be 1/3 of 7 plus 2/3, which is going to be equal to 9/3, which is equal to 3. So that checks out. So at least for these 2 points, it appears to be that this function f inverse is truly the compositional inverse of this function, but we cannot just prove it for 2 points, we have to actually prove it for a set of points. So let's actually go through a quick proof of how to do it. And remember, we can prove that by verifying that f composed with f inverse of x is equal to f inverse composed with f of x, and this is equal to x for any value x. So we need to keep x arbitrary. We can't just be picking numerical values. All right, so let's verify this first part. So this is going to be A, and then we're going to focus on part B. So A, so f composed with f inverse of x. So we know what f inverse of x, f inverse was equal to 1/3 x plus 2/3. And f, so remember what f was, so f of x was equal to 3x minus 2. So what we're going to do is we're going to take this function and we're going to input it into this function. So that's what compositions of functions pretty much did. So this is going to be equal to 3 times 1/3 x plus 2/3 minus 2. And our goal is to show that this is equal to x. So I'm going to distribute 3 into this expression, so that's going to give me 1x plus 2 minus 2. And as you see, these 2's cancel, and we're just left with x. So this part checks out. So the second part that we need to verify is that f inverse of f of x is equal to x. And of course, I leave that as an exercise to you all in case you were following along. So if this is true, so by A and B, f inverse of x is equal to 1/3 x plus 2/3 is the compositional inverse of f of x. End of proof. Alright, so that's pretty much the algebraic way of going about verifying that a function has an inverse, and or not necessarily that a function exists, but how to sort of test whether a given function is actually the inverse of some other function that's given. So let's now look at this at the graphical perspective and see if we can get anything. So I'm going to consider the relation R, which is given by the set of points 0, 0, 1, 3, and 4, 4. Actually, no, let's not go that far out. Let's go to 2, 5. So this R is a function. You should be able to verify that on your own. So this function maybe has an inverse, maybe it does not, right? So the inverse image, at least, which I'll abbreviate by f with a -1, is going to be equal to, so I'm going to swap the domain and range for each of these points. So that's going to be 0, 0, 3, 1, and 5, 2. And I'm going to graph these points on a coordinate plane and sort of compare them, the two, with one another, right? All right, so we have 0, 0, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so we have 0, 0 there. Then we have 1, 3 here, and then I'm going to have 2, 5 up here. So I have almost a linear set of points, maybe linear, maybe not. You can verify that. And then we have 0, 0 here. Then I have 3, 1 here, and then I'm going to have 5, 2 up here. So again, we have this almost linear type of trend. And also what I'm going to do is I'm going to compare this to the relation I, which is going to be the set of points 0, 0, 1, 1, all the way through 5, 5. So this is pretty much my identity relation. All my x values are equal to my y values. So I have these types of points. So if I were to graph this to scale, you should be able to see that these curves should be making a mirror image with one another for all points in these relations. So at least from this picture, if it were to draw on to scale, that R is a mirror image of R inverse about the line y is equal to x, or the identity relation. So some people refer to this line y is equal to x as the axis of symmetry. And remember that one of the special properties about compositional inverses is that f composed of f inverse is equal to f inverse of f is equal to x. Notice the comparison with this. So if we compose one point with another, we're always going to get some point that is located on this axis, right? Because remember, if this point here is a comma b, and this point here is b comma a, every time we compose those points with each other via the inverse, we're always going to get a point on the axis of symmetry, regardless of the point that we choose, which is an actual really amazing thing. Right? All right. So let's see if we can actually guess what an inverse function is without actually algebraically calculating it. So let's consider the function f of x is equal to 2 to the power of x. And if you don't know logarithms, then this is pretty a good introduction into them, right? All right, so I'm going to choose a couple points in its domain. So I'm going to pick like -1, 0, 1, 2, 3. Right? So this is going to be my point 0, comma 1. When you plug in 1, you're going to get 2, right? So we have 1, comma 2. Then all the way up here you have 2 comma 4, so that's 2 squared. Over here you're going to have -1, 1/2, and so on. So you can pretty much connect these points to get some curve like that. So this is the graph of f of x is equal to 2 to the x. So does this function have an inverse? That's a question that we're trying to answer, right? Well, this relation has an inverse image regardless, right? So if it has an inverse image, we can just swap these domain and range points around. So we have this point, which is going to be 1, comma 0. We're going to have another point over here, which is going to be 2, comma 1. We're going to have a point all the way over here that's going to be 4, comma 2. We're going to have a point down here that's going to be 1/2, comma -1. And we can extrapolate these points to get some curve like this. So of course these graphs should be symmetric about the line y is equal to x, and we should be able to pair these points together quite well if this is drawn to scale, right? So this is the graph of f inverse, and it, at least from the graph, appears to pass the vertical line test, right? So it definitely is a function of x. Now, what is the algebraic relationship of this function? That, of course, is to be determined, and we'll discuss this later, but usually we define this to be the logarithm base 2 of x. And why do we say log base 2? Because this exponential has a base of 2. But of course, we'll talk about logarithms in a little bit detail later, but at least you can see and also know a couple points on the graph of f inverse. So even if you do not know logarithms, you should be able to know from this graph that the log base 2 of 4 is equal to 2 because 4, 2 is on the graph of this relation. So that's a little bit useful. All right, so let us also recall a property that I mentioned a little bit ago, and that was the following. So suppose that f and f inverse are compositional inverses of one another. Then we have the following pair of identities. For example, the domain of f is equal to the range of its inverse, and the range of a function is going to be equal to the domain of its inverse. So let's work through an example where we can actually use this to our advantage to figure out what the actual inverse function is. And this is going to be extremely important. So let us consider the function f of x is equal to the square root of x minus 2 plus 3. So if you recall from our transformational exercises from earlier, so this is just the square root curve shifted to the right 2 and up 3. So right 2, up 3, and we should know that the square root curve has almost like a sidewards parabolic behavior, right? So our other side of the parabola will be there, but of course this is just the top side. So let's just state the domain and inverse of this. So the domain of this function is going to be equal to the interval 2 to infinity, and the range of this function is going to be equal to 3 to infinity, right? So does this function have an inverse, and if so, what does it look like and what is it? So in case you haven't realized, the domain and range flip, right? So if we were to do a horizontal line test to this graph, if we were to flip the x values and y values around, if this curve passes the horizontal line test, its inverse image should pass the vertical line test, right? As a result, since horizontal line test is y equals graphs, and vertical lines are x equals graphs, right? So that's an important observation, right? So if f is 1 to 1, then its inverse image, f inverse, is a function. So one can at least claim as a theorem that f has an inverse function if f is 1 to 1. And some people also call this injective. So if f is injective, then f has an inverse function, right? So that's useful. All right, so if that is true, clearly this function is 1 to 1, so it does have an inverse, so it has the property, so f inverse exists, and the domain of this inverse is equal to the range of the original, which is 3 to infinity, and the range of this inverse function is equal to the domain of the original, which is 2 to infinity, right? All right, so that's our initial observations. So let's see if we can actually generate what this inverse function is. So I'm going to replace f of x with just y, so we have y is equal to the square root of x minus 2 plus 3. So this represents the relation that constitutes this square root graph. So what I'm going to do is I'm going to subtract both sides by 3, and then I'm going to square both sides to sort of get rid of the square root. So once I do that, I'm going to have y minus 3 squared is equal to x minus 2. And then what I'm going to do is I'm going to add 2 to both sides of this equation. So what this is going to do is it's going to say, okay, x is equal to y minus 3 the quantity squared plus 2. So this is still almost the graph of the original, but it's slightly different, right? Remember, the square root graph is just the top of the parabola, and this is a quadratic, the complete quadratic, the top and the bottom. So this is not the same relation as the original, right? And that's an important statement to make. So note, the relation 1, which constitutes the points x, y, such that y minus 3 squared plus 2 is equal to x, and the relation R2 with the points x, y, such that, what was it, square root of x minus 2 plus 3 is equal to y. If we have these two relations, R1 does not equal to R2. You can check out the graphs of these two relations and you'll see that they are not the same, right? So how can we sort of adjust for this difference, right? So remember, once we take the inverse, we're just going to switch x and y around, right? So we have that f inverse of x at least our claim is going to be equal to x minus 3 of the quantity squared plus 2. But remember what the domain for this inverse function was, which is dictated by the range of the original function. Remember, the range of the original function was equal to 2 to the infinity, so that means, wait a minute, no, the domain of the inverse function is going to be equal to 3 to infinity. So that's what this domain of this function actually is going to be. So this is only going to be true for x is greater than or equal to 3. So you remember how to graph this. This is just going to be a parabola shifted to the right 3 up 2, and this is only going to be the right-hand side. Okay? So if we were to graph the inverse of the inverse, which is just the original function, right? So we're going to go to the right 2 and up 3, and we're going to have this. So this is f. This red graph is f inverse. And if we were to draw our line of symmetry here, it would pass through that little intersection point, right? So this is y equals x, right? So therefore, this entire expression is the inverse of the function f of x is equal to the square root of x minus 2 plus 3. And it's very important that you include this domain. So let's go back to that statement I made about a function having to be one-to-one in order for it to have an inverse function. So let's look at a graph to sort of illustrate that idea. So let's consider a basic graph, say y is equal to x squared, which all of us should know the graph of by now. So that's just a parabola facing upwards, right? So notice that this function is not one-to-one because this function does not pass the horizontal line test, which means it can only pass once. So if we were to take the inverse image of this function, which is just going to be x is equal to y squared, so we're just going to reverse the x and the y roles here. So the graph of this is just going to be this. So instead of being on the positive y-axis, so this is typically x and this is typically y, again this is x and this is y, then instead of being on the positive y-axis, now we're on the positive x-axis instead. So notice that this line also is going to rotate to give us this vertical line. So if this original curve is not one-to-one, then this inverse image is not going to be a function. So this is pretty much a graphical illustration why the statement that if f is a one-to-one function, then its inverse, its compositional inverse function exists. Now, just because it exists doesn't necessarily mean you can find it or you know what it is, but at least it exists and you know what it looks like, at least from a graphical perspective. So let's just look at a couple algebraic examples for this. So let's consider f of x is equal to the absolute value of x. So does this curve have an inverse function? So we should know the graph of absolute value, so we know that this is not one-to-one. For example, the absolute value of 4 and the absolute value of negative 4 give us the same exact numbers, so that's not going to be one-to-one. So therefore, f inverse of x does not exist, at least not in single functional form. So similarly, if we have, say, g of x is equal to x squared, so we know that this graph is just going to be the graph of a parabola facing upwards. This is not one-to-one. Therefore, the inverse function, f inverse of x, does not exist, at least not in singular functional form. Now, this is extremely different from the statement, suppose we have h of x is equal to x squared for x less than 0. So what does this graph look like? So this is going to be the graph of the left-hand side of this parabola, right? So notice that this curve is one-to-one. So that's a good thing, right? So that means this inverse function does exist, right? So let's figure out what that inverse function actually is equal to. So firstly, the domain of h is going to be equal to minus infinity to 0, open-ended, and the range of h is going to be equal to 0 to positive infinity. That can easily be determined just from the graph, right? So let's algebraically see if we can generate what it is. So I'm going to replace h of x with y. So y is going to be equal to x squared, and keep in mind x is going to be less than 0. So if that's the case, what I'm going to do is I'm going to take the square root of both the sides of this equation. That's going to give me the square root of y is equal to the absolute value of x. So remember that important property from before. And we can rewrite this as instead the absolute value of x is equal to the square root of y. So this is an absolute value equation, so we can split this up. So either x is equal to the square root of y, or x is going to be equal to the negative square root of y. So remember, the square root of y is always going to be a positive number. So remember that x must be what type of number? So the domain of h, so x is located in this set somewhere, must be a negative number. So the only way that x can be a negative number, if y is a positive number, its square root is also going to be positive, is if we are in this second category. So that means this is the one that we want. So that means x is going to be equal to the negative square root of y. Now I'm just going to reverse my x's and y's since I want the functional relationship for our inverse. So that means f inverse of x is going to be equal to negative square root of x. So this is the inverse of f of x is equal to x squared for x less than 0. Now we also need to put a range restriction on this thing. Remember, x must be greater than or equal to 0, else it doesn't exist, but we do not want this to be equal to 0 because 0 is not in the range of this original function, right? So if we actually look at the graph of this set of functions, so here's our original, right? So there's f. And remember, this is our other side that we sort of deleted. So there's its mirror image that we're not considering. So that's the positive square root. And then we have our negative square root down here. And of course, these two functions are mirror images about the line y is equal to x, right? So this is f inverse. So that's pretty nice. So that's a good, now there are these little things that you need to take care of, because remember, plus or minus square root of x is not a function. You have to keep that in mind. All right, so another property that one can generate, so if f is 1 to 1, then if f of a is equal to f of b, then we have the condition that a must be equal to b. Now, why must that be true? So we're assuming as a premise that f of a is equal to f of b. So we know that f inverse of f of a must be equal to f inverse of f of b, right? Because we know that the function is 1 to 1, therefore this compositional inverse function f inverse does exist. Now, if f and f inverse are compositional inverses of one another, then f inverse of f of a must be equal to a for all a in the domain of f, and f inverse of f of b must be equal to b for all elements b in the domain of f. So from that we get the result that we want, right? That's a nice little proof. Now, why is this useful? Well, a lot of people tend to forget this and try to abuse the rules of math by sort of avoiding this, right? So remember, negative 4 squared is 16 and 4 squared is 16. But some people think, oh, they're both raised to the power of 2, therefore this implies that negative 4 is equal to 4, contradiction. No, that's not how this works. So this is not true, since the function f of x is equal to x squared is not 1 to 1. This is the point, right? Another example, suppose we have 2 to the x is equal to 2 to the y. So can we say that x is equal to y from this case? So in this case, we can say that this is true. Why? This is true since f of x is equal to 2 to the x is 1 to 1. You can check out the graph of exponential functions because we know that the function 2 to the x is always increasing, which of course is 1 to 1. That's an easy theorem to verify. Now here's an interesting problem. Suppose we have x to the x is equal to 1/2 to the power of 1/2. Does this imply that x is equal to 1/2? And in another case, suppose we have x to the x is equal to 3 to the 3. Does this imply that x is equal to 3? So in this case, this is no. In this case, it is yes. Now, how come we have the same exact function, but we have a conditional case for when we can use this? So if you actually look at the graph for f of x is equal to x to the x, which we'll look into later, you actually have a very interesting type of shape. Starts off at 1, and we go up here. So notice that for some parts of its domain, it's not 1 to 1, but in some cases, it is, right? So one can have a function that is sometimes 1 to 1 and sometimes not. And then you can sort of have relations such as this. Now this goes into sort of multi-valued inverses, and this is usually where we introduce things such as principal branches and so on. But we're not going to get into these advanced things at this time. But at least just be aware that sometimes you can say these things and sometimes you cannot. So just be careful every time you see these problems because they're not always true and some people will try to mislead you. So I hope you enjoyed this video. This is definitely a little bit more intricate and detailed than some of the others, but it definitely has a lot of important properties that you definitely should know if you want to seriously investigate mathematics in a very deeper understanding. Hope you enjoyed.